Welcome, Mrs. Mahoney's podcast. This is our sixth one and our last one in this series for Unit 4. And we're going to finish up looking at two specific types of nuclear reactions. And these are the ones probably when you hear about nuclear that you are thinking of. And we've talked already about the alpha decay, beta decay, we have gamma radiation, the electron capture. But when you hear about nuclear energy and you hear it in the news or they're talking about a nuclear plant, a nuclear submarine, a nuclear airplane, what we're talking about is a fission reaction. Now in the sun is where we get fusion reaction. So what we're going to do is just spend a little bit and kind of compare and contrast these two so that we can understand what the difference is between these two reactions. So the first one we're going to look at is fission. Okay, you need to know these names. You need to know the names of them, and you need to know the difference between them. So fission, to split. And that's exactly what's happened. So we get the splitting, and this is when we start with a bigger, heavier nucleus, and again, nuclei, plural, and they're going to split into fragments of approximately equal the same mass. So two medium size, one big, splitting. So picture it, one big splits into two medium size. That's fission. This happens when you get a slow moving neutron and it's going to run in. So we get this little neutron coming in here, and if it hits it with the right energy, it's going to split that and start the reaction. But what happens, I get more of these little neutrons out then, so they get to go hit some bigger ones. So you get excess neutrons, and they go on to split other uranium or other big ones, and then so on and so forth. And so this is what starts a chain reaction in our fission. So one starts, but because we get more neutrons out, they're going to be able to hit, and you get more, so they're just splitting and splitting and splitting. Okay, here are some different examples. Now, if you notice, you don't always get the same products. Typically, you will see uranium-235 used as a source. It's called a fissionable, meaning it's able to undergo fission, isotope of uranium-235. So here, what are we doing here? We're hitting it with that neutron, and we get out krypton-90 and barium-143, and 3 more neutrons coming out. Okay, this is saying the same thing, but a little bit we're doing the pictures and with the words. Now look at our masses aren't identically the same. And again, we didn't write them in the same order. That's okay. Remember when we were writing nuclear, you can have these in different order. You just have to make sure all the math adds up. So over here, I've got uranium-235 being hit by a neutron. So let's look at the math. Over here, what's this add up to? 236. Okay, down here on the bottom, what does this add up to? 92. On the top, I have uranium, and I have barium and krypton. So we add these up. 141 plus 92, that's what? 233. But then we have 3 neutrons. Right here is like distributive. This 3 neutrons is the same as right here. 1, 2, 3 neutrons is just a shorthand way. So what do we say? 233 plus the 3, we get 236 on top. 56 plus 36, because neutrons, they don't have a charge, so down here on the bottom, 92. It adds up. So balancing these are exactly the same of what we've already done. It's just looking at one specific type. And again, big one splitting into 2 mediums. You get some more neutrons coming out. That's how you recognize it's a fission reaction. Okay, fission reactions, again, looking at the pictures. Let's look at some pictures. Splitting, get more neutrons, they're going to split. This is that chain reaction. It's another picture of the chain reaction. Uranium, they get our 2 mediums, because those new neutrons, they could hit some more uraniums. So then you get more, and can you just see how exponentially this really quickly can either be grown out of control, you get a bomb, you control it, you get the energy for nuclear reactors. That's the difference between a bomb and the nuclear reactor, if we can control this reaction. So what happens, this energy, that we talked about that binding energy when we started, the energy that holds the nucleus together. When you tap into that energy is released. Well, you need to have a critical mass in order to sustain any chain reaction. So when they're planning to do a bomb or when they're planning in a nuclear reactor, they need to do a little bit of the math to figure out how much do we need. Because if you don't have enough of this critical mass, your reaction is just going to stop. Well, so for you, this is just a side note. Don't feel like you have to memorize this number, but just some people may have wanted to know, okay, how much is that? Well, for one free neutron for every 200 uranium-235, that's about 0.9 kilograms is what the critical mass is. So this is when we talk about not having enough fuel. That's the thing. This is hard to come by. This is why not everybody has their own low atomic bomb or is using nuclear energy. It's not like you can just go down to Walmart and buy some uranium-235. Thank goodness. Okay, again, another picture. So the more we can kind of see it, hopefully it sticks in your head, fission is splitting. Fission is splitting. Okay, it is the energy behind the atomic bomb. Now, I'm going to kind of skip this. It says let's look at how atomic bombs work because I'm going to talk about this tomorrow in class because I have web page I can go through. It's just a little easier to do actually. This is one that would be easier to do in person than to do versus the podcast. So we will talk about this tomorrow. Okay, but in a power plant. So whenever we talk about nuclear power plants, again, nuclear submarines, anything being used, commercial applications, it is fission. Fission is the only thing that we're using for any kind of application on Earth. So we use control rods. Let's just look at some of the parts in order to control that reaction. Because we're going to look at what happens when an atomic bomb. Obviously, we don't want a bomb going off when we have a nuclear power plant. So this is how they control that. Because it really is with a little bit of source. So if we look at that, 0.9 kilograms or a small amount of fuel compared to the truckload after truckloads of coal, you can produce a tremendous amount of energy. But parts of it, you need control rods. They control the rate of it by their absorbing those neutrons. If the reaction's going too fast, they'll just absorb some neutrons and slow it down. You need fuel rods. And again, most common is usually uranium-235. Sometimes plutonium-239 is also used. But it has to be able to have the property to undergo fission. And not all of the uranium isotopes will have a chain reaction of the fission. Okay, you also have what's called moderators. And just like it sounds like, they're going to moderate or they're going to slow down the speed of those neutrons. Because we said again, it had to be a slow moving neutron that hit it. So the moderators help to control that speed to get the reaction going. And then they also, because they're absorbing the energy of that fast neutrons, we usually use graphite or heavy water, which means it's used by deuterium or hydrogen 2 versus hydrogen 1 is most commonly used. Okay, what's the problem with this? So you hear in the news, what's the problem with nuclear chemistry? If it's used little fuel source, why is it such a political hotbed? And the reason, the waste. You have a nuclear waste that is still producing radioactive. And then they're going, okay, what do I do with this? And there are people who said, let's bury it. Let's bury it under the ground. Some people said, let's shoot it to outer space. But imagine what would happen if that rocket falls down. There's people who said, just let's put it in Nevada. Nobody lives in Nevada other than Las Vegas. And they've looked at putting storage sites there. But the problem is, if your nuclear reactor is in New York, how's it going to get from New York to Nevada? So this is a big problem with it right here. It says radioactive waste. And nobody really knows what to do with it. So when you hear about a fallout, what happens is if you have it contained within that reaction, and again, this is why if you look at a reactor, these are the concrete walls to contain all of this. There's a big worry that they would have some kind of spill in this or some kind of breach. Even after the the earthquake in Japan, this was the big issue, that all their containment that they had done, there was some kind of breach in it, and that radiation was going to escape. So that is the worry with this, and why a lot of people don't want nuclear, because there is the possibility of this radioactive waste and just the radioactive going on inside of here getting out. The other problem with it is that it is a limited fuel. Because in uranium sample, less than 1% of it is actually this fissionable uranium-235. Majority of uranium sample is uranium-238. So almost 99%, a little less than 99% is uranium-238. But again, when we talk about fission, or we talk about nuclear energy, fission is the energy that's going on. We're using the uranium-238, 235, you're splitting it, it's producing the energy in a chain reaction. Okay, and again, let's kind of compare this picture again. So here's our moderators. We said, so this is taking place, usually there's graphite or even sometimes just in that heavy water. It's slowing down the neutrons. It hits the uranium and it slows it down. So these control rods is when they want to, if they want to slow down the reaction or stop the reaction, they'll insert these control rods, absorb these neutrons, the reaction will stop. Okay, these are the fuel rods, would here then be the uranium-235. These are in your fuel rods. And it'll reach a point where these you don't have enough to support fission, but there's still enough there to be the radioactive. So this is where our waste comes from. And it's still producing the radioactive and it's still producing decaying. So that's what they have to control. And the problem is the half-life on some of these, they're still radioactive for thousands of years. So that's why you can't just store them for a month or so and then they're safe. It's something that you have to look at for the long term. Okay, let's compare this to fusion then. Okay, fusion. Fusion is just what it sounds like. If you fuse something together, you're gluing them together. Fusion is them coming together. So here we're going to start with two light radius and they're going to fuse them together, and so you're going to make something that's just a little bit heavier. Okay, the number one place this happens is the sun. This is the energy of the sun. So think about how the sun can heat all of Earth. You know that that's producing a tremendous amount of energy. That the fusion produces more energy than a fission reaction. So much that the hydrogen bomb was the energy was used, we used a fusion. And again, tomorrow we're going to compare both of these, so we'll talk a little bit more about it. But just to say the energy for this fusion bomb was contained about a balloon size of hydrogen. That was it. About a party balloon size of hydrogen could do that much damage. So there's great potentials there, but we're going to talk about some of the side effects and why this is not being used. This is not a commercial application. Obviously, this is not a commercial application. This is destruction, not something we're using to provide energy for a city. And so what happens, there's some, like I said, there's a good side. There's no radioactive waste in this. If we look at our reactions, the most common one we see, deuterium, plus we either do, there's two deuteriums, so these are hydrogen 2s, the official name is deuterium. And what do we get out of this? Helium. Helium, and a tremendous amount of energy. So you look at this, this is very clean. This is hydrogen, no problem. This is helium, no problem. So there's no radioactive waste. Another very good thing is the fuel. Well, look around us. We have water surrounding us. What's water made of? Of hydrogen. So there's plenty of fuel. So it's like, okay, well then what's the problem? Why aren't we using this? If there's no really side effects, well, look at the sun. That's the problem. You need a tremendous amount of energy to start a fusion reaction. When we talk about the bombs, we're going to use a small atomic bomb to trigger a hydrogen bomb. So you need to use a small fission reaction to trigger the fusion reaction. And think about the sun. So if we said it's the energy of the sun, you tell me what kind of container that we can have here on Earth to hold something the temperature of the sun. That's why we cannot use fusion here on Earth. Now they're looking at it, and they're looking at using like a magnetic and trying to use magnetic fuels to contain it. And I think I read that they had found some success on a very small scale, but it costs so much to contain it that it was still nowhere near economically feasible to do something like that. And then cold fusion, that's something that every once in a while, every couple of years, some scientist or somebody would say that they have created cold fusion. It's kind of like that oxymoron. It doesn't exist. That's really doesn't happen. But if for some reason cold fusion wasn't a myth, that would definitely make that person rich. So that's why every so often somebody claims to have conquered cold fusion, but they can never prove it, and it's something that they could never again. They can't actually show the experiment. They just try to sell you the idea. So if somebody's trying to sell you cold fusion, it's kind of like a bridge in Arizona. Don't buy it. So let's look at a picture then of the fusion. So look at what we have. And again, these D's. This just means it's hydrogen 2. One proton, one neutron. One proton, one neutron. And what do we get out of it? The 3,2 helium. And a lot of times this neutron is also come out. Another version of it is using tritium, which is hydrogen 3. And it says it's going to react with a hydrogen 2. So just two different isotopes of hydrogen, and you get out helium, and again, that neutron. So there's not just one type of fusion reaction, but look what we have. Two very small light forming one slightly heavier. Two very light forming one slightly heavier. So let's do a quick comparison again, because you need to know the difference. Fission, big heavy, splitting into two medium. Fusion, two small hydrogens, typically again hydrogens, fusing to make one larger. And I don't know why this says hydrogen, because this would be helium. And again, tremendous energy in both, but this has more energy. More energy. But this one up here is where we have our commercial applications. This is what's driving the nuclear sub. This is the nuclear reactor. Okay, this was the atomic bomb. This was the hydrogen bomb. And again, we'll talk more about the bombs tomorrow in class when we're looking at that. So that's where we're going to start tomorrow in class. We're going to look at the difference right here of these two and look at some of the application, and again just doing some more compare and contrast between the fission and the fusion and practice some balancing of those types of reactions. See you tomorrow.